thanks a lot for staying so long until the last session. I promise it will be a little lighter than most of the talks, and the title was Optimal Control, Tomography and Visualization of Quantum Information Processing. Actually, most of the time I talk about the tough stuff about the optimal control and tomography. Usually then I don't have time to talk much about the visualization part, and we have been working on that for many years now, and it's really actually close to my heart. So I decided, since we had some posters from my group about the optimal control part and tomography part, I'll entirely focus on the visualization part. And there will be not many formulas, but maybe something to appreciate how visual we can make quantum mechanics. So in general, when we think about quantum teaching, quantum mechanics, or in particular quantum technology, quantum computing, of course, for physicists, it's relatively straightforward, but now there's also more and more engineers that are needed as a workforce to help building quantum computers. Actually, there are programs for schools, outreach activities, even for the public. And then there's this huge gap between the kind of the simple pictures people usually use, like kind of some hand-wavy stuff, and then the actual theory behind it, and usually we don't have a very good connection to that. But I will try to show you a visualization scheme that I think is very suited to actually bridge this gap in a very nice way. Okay, so just we all know that what is special about quantum computers, and so I will talk about bits from bits to qubits. And one nice feature about the visualization that I will present to you is that it has a very, there's a seamless transition we can have between the classical visualization of classical computing and quantum computing and quantum bits. And then, of course, there's something new. We have superpositions, quantum gates, entanglement, collapse of wave function, quantum algorithms, and I will touch these points as we go. Actually, I don't see a clock. Could you just tell me 10 minutes before? Okay, so let's start with the classical qubit. We all know it can only have two values, 0 or 1, and we can actually visualize that easily. For example, you could have a light bulb, and actually here, a light bulb. I can remotely control that. You could either use, this doesn't even work. Let's just check. Well, it doesn't even work. Well, the first demo already went wrong, but you didn't miss much. But there will be more objects I brought to make things a little bit more vivid. Okay, so you can think of just having a light bulb, which either shines like a traffic light, red or green, and red is for stop, so 0, and green is for go, so 1, and with that you can easily visualize the state of a classical bit, so there are only these two values. Okay, and we have in classical computing, we have single bit gates, and one is, for example, this NOT gate. Actually, since we only can change 0 to 1, that's the only single bit gate we can have. So here, the NOT gate changes 0 to 1, so red to green, and similarly green to red, so 1 to 0. Okay, and so then we can look at also 2 qubit gates. So 2 bit gates, so classical computing, and one would be this controlled NOT gate, where we apply a NOT, in this case on the second bit. If the first bit is not 0 but 1, so if it's like red, stop, nothing happens here, but if this is 1, if it's green, then this NOT operation works. So here you see, here nothing happens, just green stays green, whereas here red switches to green and green to red. And of course you all know that, and I don't assume that I teach you anything new, but I just want to give you the kind of reasoning one can give to even lay people or people who are not really experts in quantum computing. Now, in quantum computing, what we can do is, there are many different ways to represent a quantum bit, and we have been experimenting with many, and many people have been experimenting with such representations. if you just look at a single qubit, single spin 1/2 part, for example, we know we can express this completely by a Bloch vector. And we could do all this visualization with the Bloch vectors. We as physicists, we are used to that. But I promise you that I will have a seamless transition between the classical and the quantum world. So rather than representing spins like with a vector, actually, we can physically what we can represent is the dipole potential of for example, a magnetic dipole of a nuclear spin. And if you plot that around the sphere, around the spin, then you have this such a positive and negative values. And again, we can map this on red and green. And this is what is shown here. So basically, if the spin is in qubit in state 0, then we orient, or this ball is oriented like this, like the red part is oriented just as the tip of our Bloch vector. And from the top, we just would see this red kind of traffic light. And if it's 1, basically it's rotated. We have the green pointing up. And if we look at this from this top view, we see this green disk, basically. Okay, and now what we can do, usually we don't, and actually I will come to the physical interpretation, like all these pictures are nice, but all of this actually, and I just want to stress this so I don't forget during the talk, all this is, we have a rigorous mathematical mapping between the quantum states, and actually it turns out any quantum operator we can map in such a fashion. It just happens to have these very nice properties. So it's completely rigorous, and in fact, what these colors here mean is that it corresponds to as for physicists, is the expectation value of the polarization operator, so Pauli Z, sigma Z, in each of these spatial directions. So, for example, if we measured along the z-axis, in this case, we would have an expectation value of 1, and if we measure down in this direction, it would be -1 if the spin is oriented, if in state 0, it's oriented up. Okay, and usually, basically in all, practically in all quantum computing and quantum technology experiments, we measure along the z-axis. So we have a special setup. So basically the z-axis, which is sort of the north pole here, that's of most interest for all what comes out in the end out of the experiment. And so basically we can, what we also look at is actually zoom in a view of this North Pole region and just spread this, you can think of, it's a meter around the North Pole basically, and we just map this color. So this actually brings us exactly to the picture that we had for the classical bit. And so that's basically, there we can now make this smooth transition. So, this is kind of the zoom. Actually, this is the non-zoomed version, seen from the top, for example, for this NOT operation. And we can have the same picture, actually, if you just look at the small small region around the North Pole. And then we have this picture, which is exactly identical to what we looked at the classical bit. Okay. So, of course, quantum states are not limited to computational basis states, 0 and 1. That's where all the power comes from. We also can have superpositions and entanglement. I'll come back to the entanglement in a second, but let's start with superpositions. What do superpositions look like? Actually, if you're familiar with the Bloch vector representation of quantum states, we know a superposition actually corresponds to a Bloch vector, for example, pointing in the transverse plane. And similarly, basically this sphere just does the same thing as the Bloch vector. So in this case, we have superposition of states, say 0 and 1, which we can create by such Hadamard gate, for example. Then we find this Bloch ball, or actually what we call this, we have a very general mapping we call the drops representation, and the acronym doesn't matter, but basically since these things look like little drops, and so this corresponds to the droplet of a single qubit. And again, we can do different operations, actually the same operation, but starting with different operators. And now you see, if you look at the zoomed top view, basically here we see black, and here it's also black, basically. And remember, black. This means that what we measure is the expectation value of sigma z, and here this is just 0 in this experiment. So we have the same probability in the end to measure spin up or spin down, and if we measure many times, basically the expectation value is 0. Okay, and these are just concrete expectation values for different qubit states. For example, here we see, if you just look at the North Pole, for example, these two figures are exactly the same, but they do represent different states of the qubit. Here we have an I rather than a 1. So if we want to have the full information, basically we can look at this picture. But oftentimes we get kind of the essential information also by simplifying the picture and just looking at this zoom view. And so again, this just was to kind of give you an idea what we are aiming at or what we are trying to do. This representation actually, so again, we call it the drops representation. This is another version which is called props, and I will not go into details. Basically, it builds on a huge history. On the one hand, it turns out these are kind of generalized cases of phase-based representations, for example, Wigner representations or Glauber Q representations. There are all kinds of different cases. Of course, built on quantum physics. It's deeply rooted in group theory. There's a lot of symmetry arguments, how we design these basis functions that we use for this mapping. But the nice thing is all this theory, basically, we can keep below the surface. And if I want to teach quantum, or want to give a sense of the power, what is the difference between quantum information processing and classical information processing, I don't need to go into there. But of course, there's a lot to be explored here. Okay, so basically this has started, this whole work, about 20 years ago with the first experiments. Then a student, actually a mathematician, Ariane Caron from Canada, she did a PhD work project in my group. And initially, kind of this mapping was easy for 2 qubits, but for 3 it was already getting hairy, and it was not clear how to extend this to arbitrary number of qubits, and that's where group theory comes in very seriously. And so basically, what we managed actually to find a general mapping of states for also coupled for coupled qubit systems, and also for coupled spin systems. And there's a huge range of applications for this. Actually, most of, as a side remark, most of the pictures you will see are like this, that there are like red and green spheres. This actually is one of the things one nicely kind of captures with this visualization. Whenever when we use this general mapping, whenever we have Hermitian operators, and basically to map the states, what we do is we map them to the density operator, which we can always do 1-to-1, and then the density operator is the Hermitian matrix, and all these Hermitian matrices have just real values. But if we look at other operators like propagators, quantum gates, they can be non-Hermitian, and then you get more colorful pictures. And just to indicate, so again, there has been a lot of work. So this first paper by our group in this direction was from 2015, and then there are many more topics we studied, but these 2 papers are the most important for the visualization, and basically we can visualize arbitrary quantum systems. Of course, still quantum mechanical state space grows exponentially, so we'll never be able to map something with 50 qubits, but for a handful of qubits, which are actually very interesting, or which are very good to explain basic concepts of quantum information processing, maybe in teaching or also to the public. That is, I think it's still not too complicated, and one can nicely work on this. 8 years ago, actually, we published the first version of a program, of an app, basically, we developed. And when I say we, it was Niklas, who is in the audience, who is doing his PhD now in the group of Stefan Philipp. and he more or less single-handedly at the time programmed this app. Of course, I was helping because he started with this having no idea about quantum mechanics and basically learned quantum mechanics implementing this app on the way. And he has been spearheading the development of this program for several years, and now other people, other students in my group have taken over, and most recent versions are developed by Dennis Huber, who's certainly in the audience. I just don't see him right now, but okay, here he is. Okay, and actually, so what is nice about this, so we had this mapping, and we had the visualization, so we can use this mapping and implement it in, for example, in MATLAB or Mathematica, and it works. But each of these figures, to render them takes, several seconds or maybe half a minute sometimes, depending on the complexity. So we could not do fluent movies or interactivity. And basically what we have done, what this app does, actually, it collects a lot of tools and very fast computer graphics, and so basically it's available for free. One can download it. Actually, the figures I will show you is a beta version, which is not downloadable yet, but soon it will be, and it runs for Mac OS, Windows, basically for all operating systems that you will have. And here just a small glimpse of the mapping that we use, again, without going to the mathematical details. Whenever we have an operator, for example, for states, we look at the density operator, but again, it could also be Hamiltonian, a propagator, quantum gate, or whatever. We can decompose this into a special set of sub-operators with this label L. And so what is nice about this is we have sub-operators, for example, that contain spin operator terms only acting on one, for example, on qubit 1, and other subset only on acting on qubit 2 or qubit 3, or bilinear terms, so 1, 2 correlations and or 3 spin correlations. So basically, these are kind of sorted according to this. Then these can be decomposed as a linear combination of spherical tensor operators, which have been mapped 100 years ago according to the properties of spherical harmonics. And basically, if you just take these coefficients of these spherical tensor operators, and so that you get after this for this decomposition, and you then combine with these coefficients spherical harmonics, you get these pictures here, for example. And actually also just something so you're not confused. So we have this. That's probably you've seen this many times. So spherical functions, you can always. There are many ways to represent them. You can actually represent them as functions coded in color on a sphere, or you can actually implement sort of the magnitude by the radial distance from the origin. So basically, these are just the same thing. And in the NMR setting which we started out with, we focused basically on this kind of representation. But as you've seen with this transition from the classical computing in quantum information processing, I think it's very nice to go to this spherical representation. Okay, and then basically we can arrange them here, which is shown a little more in detail. We have linear terms, basically. So there's one, again, we call droplet, corresponding to operators acting on spin 1, one droplet on spin 2, on spin 3. Then there are droplets corresponding to correlations between these. So these are 3-spin correlations and identity operator. And then these are combined. And just before I come back to the quantum information part, let me just show you visualization for an example from NMR. So in NMR spectroscopy, we have quantum evolution, so it would not be possible without quantum effects. But we have a highly mixed system, and so we actually cannot. Originally SpinDrops was really tuned to the NMR setting, and what we are doing right now is to also write a new version, and we're in the process of this. It's not. There's still a lot to be done, but there's we are trying to adapt basically the language and nomenclature that is used in quantum information processing, rather than the typical jargon or nomenclature that is used in NMR. But again, and one characteristic difference is that in this previous versions of SpinDrops, we didn't consider collapse of wave functions, things like that, which just don't happen in the ensemble. Here, what I would like to show you is just the quantum jump, basically, that you get by looking at such transformations. Here's a simple NMR experiment. It consists of 6 pulses. Here's the initial density operator represented as a matrix. And so let's just see what happens during this experiment. So the elements of the density operator change. And the pulses have a lot of activity. And in the end, we get this density operator, but well, unless you're an extremely trained person analyzing these pulses and understanding what is going on, it will not be obvious at all. I mean, typically what NMR people do nowadays, or until we had SpinDrops, was to look not at the density operator, but actually of the individual expectation values of some of the operators. And then basically what one sees that well, originally we started with operator on spin 1, and now we end up with a term on spin 2. Okay, now let's finally look at exactly the same experiment with SpinDrops. So let's start. Okay, so we see there was something on spin 1. This distributed in 2-spin correlations, 3-spin correlations. Here, everything was refocused to 2 spins, and we exactly, this is by design. And in the end, the experiment brought us from polarization on this spin to this spin. And so it just gives a very different view. And I mean, of course, people who have 10 years of experience, they say, well, I mean, I knew all that. But people who start NMR or quantum mechanics, they're very appreciative of such tools. Okay. Now let's go to the entanglement. So we looked at the qubit, how to visualize that. We looked at superposition. That was easy also. Now what about entanglement? So here is a representation, again, with this kind of top view. We have 3 qubits, and we look at the 2-spin correlations, like saying that we plotted before. And what we change here is this angle. Basically, it's the Schmidt angle of this superposition of 0, 0 and 1, 1 state. So actually, when we change that, I mean, one thing we see is that the polarization on the first qubit, actually, initially it's 0. If this is 0, this is increasing. And here, this one, well, they're identical, and this one also. And here, the correlations between spins 1 and 2, it's also changing. And initially, when we looked at this, we thought, well, I mean, do we see entanglement? Are these correlations that we see, is this entanglement? Can we directly see entanglement? The answer is no. Actually, I mean, we saw kind of indirect entanglement because these single qubit droplets, basically they correspond to the reduced density operator. So if this is not complete, then we know there must be entanglement. But what we see here is not directly entanglement. And but there's actually a literature which we more or less found by accident, which I think is not very well known. Actually, started in the 90s by a group of Schliens in Stuttgart. They they actually found a general way to separate classical and non-classical correlations. And it turns out that in the case of pure quantum systems, which we are interested in, at least in teaching, like, of course, when it's getting realistic, will not be pure, I mean, again, but for the teaching purposes, we can first focus on the pure states. Then, very simply, one can actually subtract classical correlations, and what remains, these non-classical correlations, actually do correspond to entanglement. So one can see there's a one-to-one correspondence between entanglement, so that basically we cannot separate the states into a tensor product of 2 single qubit terms. But this kind of matches exactly to this. And just want to point out that, I mean, this entanglement visualization was also a topic of one of the posters. In this case, a poster by Dennis Huber and Amit, who's the chair of the session. And there actually we use this separation also to experimentally measure entanglement in the system and what kind of entanglement you have. And let me just, again, without any formulas, just illustrate what is, what is behind this, and it's actually quite simple. Entanglement, correlation is something which sounds interesting or non-classical, but actually there's a lot of classical, or let me call it trivial correlations, which we don't care about. So let's look at this experiment. Suppose we have two black boxes. All we know is there are red and green, all green balls inside. So we take out boxes, and the only outcome, for example, this experiment is two red balls. So there's obviously a correlation. So if one is red, the other one is also red. Whereas here we have kind of mixed things. So we have all possible combination of red and green, so red, 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 green, and so forth. And we have this experiment where red always comes with red and green with green. And now, of course, here this was not surprising, because if it's always red, there are only red balls in this thing. So all this is just kind of trivial correlations. The fact that these are the same is nothing mysterious. Here we just get all the combinations. So that's here we don't have any correlations, but that's also not a surprise. Here actually we have a mixed bag of red and green balls, but these correlations is extremely surprising. So with such a bag of balls, you would not get that result unless you play some, do dirty tricks. So basically that's what is the magic that is used also in quantum information processing. And these are kind of the typical correlations, and the non-classical correlations that correspond to entanglement. Okay, and this was just the slide I showed you before. And what we can do, and you see that they're always, like for all these Schmidt angles, actually, we do see correlations, but this was the total correlations consisting of classical and quantum correlations. And now what we can do is we can filter out the classical correlations, so we only see the non-classical correlations, and you see for this angle, so for this angle, we see actually maybe it's mixed up. I'm not sure right now about probably this should be 0, but it doesn't matter. For one extreme, so when we have, for example, the full Bell state, so if this coefficient is the same as this, then actually this should be this case. Then there's no polarization on the individual qubits, but we have this entanglement, whereas this goes away if we are just, for example, in the 0-0 state, which would correspond to this case, where we have no entanglement. So there's still a lot of, as we have seen before, there's still a lot of entanglement, a lot of correlations, but not no non-classical correlations. And so actually then we can separate entanglement, so basically non-classical correlations and classical correlations. So for example here, this case, there's only classical correlations, and if this angle now is pi/8, we have basically both classical and non-classical correlations, and here everything goes into non-classical correlations. And okay, so we have seen these kind of pictures now. So we have, in this case, just a situation where we where we are in the state 0-0, so both spins are spin up, so like this. Here we have one spin excited, so it's rotated like this, and here we have created this entanglement between them. And actually, this sequence of event is at the heart of one of the most widely used way to create entanglement. And actually, so it's a top view simply. And what you do is you go from here to here, you apply a Hadamard gate on one of the two spins, and then a controlled knot between the two spins, and that creates this entanglement. And I will show you a SpinDrop simulation of this in a second, but I will show you just because so that I don't have to switch back and forth so many times. I'll show you one more example where entanglement plays a crucial role, and that's teleportation. Okay, if you are like me, well, you always read about teleportation, but going through the math is kind of tricky and boring, and in the end, you maybe don't learn so much by going through the math. So maybe it's the first time you see a visual representation of what is going on in an entanglement in a teleportation experiment.
So we have 3 qubits. Here we have these gates, these measurements, and some operations. I'll just go through this step by step. Actually, it turns out that, so I draw this line. So these 2 qubits I consider as my 2 qubits, and this line should symbolize that basically there's a partner who owns qubit 3. So you could be at the other end of the Milky Way and we are trying to communicate. And what I would like to do is to send you the state of the first qubit, of qubit number 1, of the first of my 2 qubits, to send you this to your qubit. And here's a visual representation. Basically, I mean the 2 qubits in the front, these are my qubits, and this is your qubit. So we start out by, before you left to the end of the Milky Way, we created entangled pair of qubits. So just like I showed before with the Hadamard and the controlled knot. Then you go away with your qubit. You see there's no polarization on this qubit, but still there's this entanglement between the qubits, even if you are very far away. And now I create, or I have this state. I try to put it in some arbitrary angle, and we want to transfer this state to the qubit number 3. This. So this is the state of interest. And so first what we do is we apply a controlled knot gate to this. So this creates this picture. And again, I just look at picture now. I mean, of course, you can do the math and see the correspondence. So basically what we have created here is we have still have entanglement between 2 and 3. But we also have 1-2 entanglement, 1-3 entanglement, and entanglement, actually we have created entanglement between all 3 particles. Then there's a Hadamard gate, which actually let's just go back and forth. So things have changed, but at first view we don't see so much. Actually, we see this one was before along the z-axis, and now it's tilted like this. And then we do a measurement. I mean, we actually do 2 measurements. We measure qubit 1 and 2 and qubit 2, and we get 4 possible outcomes. I mean, qubit 1 and 2 could be both 0. 0, 1, 1, 0, 1, 1. And if we look at the qubit, I mean, so a lot of stuff has collapsed, but if you look at the qubit of U, at the other end of the Milky Way, basically what we see is, well, okay, the experiment went right in this case, so we found exactly the same state, but these states are not quite right yet. So what we do now is, and actually, so these kind of, I mean, usually there's this picture of wave function collapse. You can think of different worlds that are created. I mean, so here with SpinDrops, we can represent these different worlds. In this case, they have all the same probability. But now we have these operations. So if the second qubit is 1, and we send this information, so these are classical channels. So I measure this and send this to you. And then if the outcome, for example, of qubit 1, if the measurement is 1, then we apply this NOT operation. And in this case, actually, here it is, qubit, actually 2-bit Q, yes, so this is 1. So actually, this is changed. See this? And here, actually, we have corrected this. And then we have another measurement. So I measure the state of, the projection of qubit 1 along the z-axis. And we see here that's the case in this world. In this world, here it's 1, 1. And then if it's 1, we apply a Z rotation. And this kind of corrects this for all the possible outcomes. So in this way, by going through these steps, actually, we can basically send this unknown state to your friend. And we only need to convey 2 classical bits of information. And so let maybe just switch off. This works now here to SpinDrops. Okay. So what I just want to show you a little bit, just give you a flavor how this works in practice, working with this program. Actually, it's if you are used a little bit. Get used to the setting. Okay. So it's very responsive. Actually, let me just first go through this. Turn this around. It's not too counterintuitive. So here, for example, here we still don't have a good. One thing that's missing is to create these gate sequences. Here it's a little bit inconvenient, but all this will come. Here we apply a Hadamard gate on the first qubit. So this was this first qubit. Then we create this. Actually, here we just have NOP, means no operation, just so we see. Keep that for a second. Then we apply a controlled knot, AB. This creates this entanglement between the two qubits, and polarization on the qubits goes away. And actually, there's another operation that I do in the end. I'll just run it. Oops, sorry. What did I do? Let's see. Somehow it's not mirrored here on my screen, but okay. So let's just run this again. Now just run the full simulation, and then we see the different steps. And in the end, actually, there was a 180-degree Y pulse applied to spin A, and actually we created these Bell states. And with this operation, we create from the Bell state, basically, which was this state, which only in certain directions gives us positive expectation values for bilinear correlations. We created this, basically that's the antisymmetric Bell state. And in this case, actually, you know this, but it's difficult to see by eye, that here you can measure in any directions, you always get anti-correlation. So if one spin, you measure spin up, the other one will be spin down, and vice versa. Okay, so let me just wrap up with final slides. So here. Okay, so you've seen the SpinDrop simulations. Here's just an example that we can also distinguish the kind of entanglement. So for example, W state and GHZ state look very different once you've seen them. Also, what could be a drawback is it's difficult to draw these things, but we can also draw kind of pictograms of this. Here's a different way to represent these things, also props representation, which is, has been developed also by Dennis Huber, who, and with this we were able to predict basically the outcome of measurements by looking at the state before the measurement. And basically we looked at all these different parts. Hopefully you have seen the poster by Amit, Niklas, Dennis, from my group about Wigner state and process tomography on near-term quantum devices, in particular on how to do that efficiently and conveniently on IBM devices. One actually can, so these are simulated droplet representation, but you can do experiments and actually scan these droplets and recover these shapes. Actually just from the experience I have, so I have used this drops representation and these droplets in the NMR setting in a lecture that I give. It's called Quantum Mechanics Basics of NMR Spectroscopy in Munich, and it was considered to be very helpful to have this. So this was 2019, great Ergänzung, completion of the lecture. Was helpful to visualize the theoretical calculations. So it's always good. Ideally, you combine this with calculations, and it's also fun. 2020, 21, also very favorable comments. 22, also very good. And very well received. And here's a test we did with high school students, actually female students, in Thum and Deckerin, and they also, so there we didn't do any calculations, so it was only visualizations, but to convey an idea of the mechanics behind that. We also have some devices to show now these shapes in 3D. Here's a picture of the group. So I mentioned Amit, and Dennis. Here's Leo, who had the poster on analytical tools for optimal control in 3-level systems. And actually, Patricia König is studying a lot of these quantum algorithms right now, and to see how, if it's beneficial or not to use SpinDrops. Here are cooperation partners, but all this is projects for which I didn't have time to talk. Here are the funding agencies. And maybe one day we even have drops representation on a big scale, like here, which is a radar station on Madeira. Okay, thank you.
Thank you, Steffen, for the nice talk and the nice, colorful droplets. Is there any questions from? Yeah.
Thanks for a very nice talk. So I just have a very small question. Just to start, I'm not an expert on this, but there's a famous work I know by Ignacio, which showed that, back in decades ago, like he showed that, there are different inequivalent way of actually entangle, say, 3 qubits, right? So they actually, there exists a finite number of inequivalent classes of where you can entangle 3 qubits when you only allowed to do local operations and classical communication. It's because apparently my understanding is that you have proposed or you have created a way to sort of very nicely visualize sort of like a generalization of block sphere for a single qubit to sort of multiple qubits. So now you have a very intuitive way to understand what are the possible structures in these multiple qubit states. So is there a way, first question is like, is there a way to sort of intuitively picture why, picture the different entanglement structure in say 3 qubit system? And then is it possible to also shed insights into how to sort of, can you identify more richer structures in entanglement in more, say, 4 qubit system or 5 and things?
Yes, so actually we are very interested in this topic, and maybe if you are interested, it could be great to talk in more detail. Actually, a student who's now in Christian Mendel's group, she did her master's thesis in my group, and was exactly about, her project was to study these kinds of classical, this kinds of non-classical correlations, entanglement, and so as you've seen, visually we see a difference between these terms, and you can then also find entanglement measures based similar on the norm of these non-classical terms. But Schlins has suggested that already 20 years ago or even longer. What one can do is, and what we did is, now we have these different droplets, and for some droplets are populated, for example, by the GHZ state, but not by the W state or vice versa. And they're different. Actually, there are different ranks. So you actually saw very different symmetry of the two terms. So one can basically decompose this into the spherical tensor terms. Now we can look at the distance or the projection, the maximum projection we can get under local unitary transformations from one to the other. So we see much more structure than I think it was before, and now we have maps like, what is the distance between these terms? But of course, all these things have to be done simultaneously, and it helps a little bit, but we don't have a complete solution yet, so that's why I'm very interested to maybe continue along this.
Thank you.
Any other questions?
Thank you for this presentation. My question is whether there is a way to maybe derive expressions for the entanglements in a very useful way that one can use for characterizing the quantum system, for example.
Yes, so one can derive entanglement measures based on this. Basically, you just calculate the norm of all these droplets corresponding to non-classical correlations, or the norm of the non-classical correlations in the system. And we actually have, for a 2-spin system, it's easy. We can always calculate this numerically, but for a 3-spin system, we didn't succeed to find a closed-form expression for this for the most general case. It's also one of the open problems, and if you're interested in this, I'm happy to talk about.
So it's possible to maybe derive a string of inequalities. Looking at the shapes, then you can characterize the interaction between different spins. For example, in many-body systems, is it possible?
Maybe, but I'm not sure right now.
Okay, thanks.